Welcome viewers to the fourth segment of the seventh lecture for the online series of lectures for the course of linear algebra. We were with part C of lemma 1. Um, so we can write this left hand side as what we have written on the right hand side. So this is what we have here, and so we can do this since ut1. We can do this since EU composed with t1 is a linear operator on the vector space V, and this linear operator, this set of linear operators on the vector space V is an F vector space. Okay, so the scalar multiplication in this vector space is defined by means of equation 19. Scalar multiplication in LVB is defined by means of 19. Okay, so now we use the definition of composition, and that will let us write this as CUT1 of V. Okay, using definition of composition in Theorem 5. Okay, so this is equal to Cu acting on T1V. Okay, so here I use 19 again, since I can do that since U is a linear operator on the vector space V, and LVV is an F vector space. Okay, so we are good, and so now using composition again, Cu is an operator, and that operator gets composed with T1, and the whole thing is evaluated at V using back the definition of composition. Okay, so we started with the left hand side here, and we arrived here for any vector V in the vector space V, so that Cu composed with T1 is equal to Cu is an operator, linear operator, and that gets multiplied with T1. Okay, good. All right, so now there is another part in part C, for which we start with C is the scalar C times U composed with T1 acting on V. That's the left hand side. and that is so we use composition here. Okay, so first of all we write it as C ut1 acting on V. Okay, this why can I do that? Because ut1 is a linear operator, and you know, and LVV is an F vector space. So we use the scalar multiplication structure here. Scalar multiplication rule here by 19. Okay, good. So this is C U T1 and this is equal to UT1, sorry, this is equal to UT1, sorry, yeah, so this is C U T1 of V. This is what we do using composition. So then, right, now you see that U is a linear operator, so we use the linearity of U to write it as C of T1 of V. Use linearity of U. Okay. So now we can write it as U of C times T1 is an operator and that acts on V. Okay, and here using 19 since CT1 is a linear operator given C in F and T1 in LVV. So by using composition, this is going to be UCT1 acting on V, using back the definition of composition. From Theorem 5. Okay, so this was the left hand side and we arrived here, which means that C times UT1 is equal to U times CT1. Okay, this was the second part of part C. C of C times UT1 is equal to, yeah. Okay, so we are done proving lemma 1. Now, what was theorem 4? Theorem 4 states that if V and W are finite dimensional vector spaces of dimension n and m respectively, then the vector space of linear transformations from a V to W is finite dimensional and is of dimension m times n. That was theorem 4, and we just prove lemma 1. So theorem 4 and lemma 1 together tells us that the vector space of linear operators on V together with the composition together with the composition defined in theorem 5 is a linear algebra. I think it's not theorem 4, it's theorem 5. We require only theorem 5 where we define the composition. So theorem 5 together with lemma 1 tells us that the vector space LV comma V, that is the vector space of linear operators on the vector space V together with the composition defined in theorem 5 is a linear algebra with identity. The identity is the identity transformation. Linear algebra with identity. Okay. Good. Now I'll give you an example at this stage, which is example 5. Let F be a field and V be the vector space of all polynomial functions from F to itself. V be the vector which we denoted earlier by calligraphic P. Now we are using a different notation for the same vector space. V be the vector space of all polynomial functions from F to F. A general element of this vector space V is given by V of x, which is a polynomial, is c0 plus c1x plus c2x squared plus all the way up to cn x to the n, with all these ci's in the field F for I between 0 and n. Okay. Let D be the differential operator on V given by, how does it act on a polynomial? dv, okay, dv, well, evaluated at x is equal to c1 plus 2c2x plus all the way up to ncn x to the n minus n, x to the n minus 1. Okay, so we call it equation number 20. All right, and on the same vector space of the polynomial functions from F to itself, we have another operator which is called the multiplication operator, which we denote by T. T be the multiplication by X operator multiplication by, so I think it's better to write it as dvx, the way we did it in the lecture material. So multiplication by x operator, that is tv. Okay, so tv is a polynomial function. Okay, tv is a new polynomial function, which is expressed in this way. dv is a new polynomial function, which is defined, which is given by this expression. Okay, so tv is the new polynomial function, which is given by tv of x is equal to x times v of x, which is c0x plus c1x square plus c2x cube plus all the way up to cnx to the n plus 1. This is equation number 21. Okay, now I leave it as an exercise for you to check that both these operators are linear. That is, you need to verify that dt are linear operators on the vector space V of polynomial functions from the field F2 itself. For example, let us see, given alpha, a scalar, verify t of alpha vx plus wx is equal to alpha t vx plus t wx, where wx is another polynomial, that is w is a function from f2 itself, given by w of x is equal to okay, yeah, w of x is equal to d0 plus d1 x plus d2 x squared plus dmxm, where m and n are in general different. They are polynomials of different degrees, v and w. Okay, it's easy to see that t of alpha v of x plus w of x, remember what is v of x? V of x is equal to c0 plus c1x plus c2x squared all the way up to cnx to the n. So according to the definition of this linear operator t, this is going to be x alpha v of x plus w of x, which is equal to alpha x v of x plus x times w of x, and according to the definition of the linear operator t, it's going to be alpha t v of x plus t w of x. Okay, So which proves the linearity of this multiplication with x operator. Okay. Um, Now also you can check that dt minus td is equal to the identity transformation or identity operator on the vector space V of all polynomial functions from f to itself. In fact, d t v of x is equal to d. So what is t acting on v of x? Well, it should be read as t acting on v evaluated at x is x times v of x, right? So x times v of x is c0x plus c1x squared plus c2x cubed plus all the way up to cnx to the n plus 1. Okay. And when the derivative operator acts on this polynomial function, one obtains c0 plus 2c1 x plus 3c2x squared plus all the way up to n plus 1 cn x to the n. Okay, and td v of x is equal to t, and now I apply the differentiation operator on the polynomial v of x, which gives us you know we know what is dv of x, right? Dv of x is c1 plus 2c2x plus all the way up to, so let me write the third term as well, 3c3x squared, right? 3c3x squared, and finally what we have is n cnx to the n minus 1, right? N cnx to the n minus 1. So now I apply this operator, the linear multiplication by x operator, to this polynomial dv of x, which gives me x times c1 plus 2c2x plus 3c3x squared plus all the way up to n cnx to the n minus 1, and this is equal to c1x plus 2c2x squared plus 3c3x cubed plus all the way up to n cn x to the n, right? So now I subtract this from this, okay, so that I have dt v of x minus td v of x to be equal to c0 plus c1x plus c2x squared right, all the way up to, this is n plus 1 cnxn, and this is ncn. Sorry, these are multiplied with, so this is not combination kind of thing, it's n times Cn is the coefficient. Okay, so okay, this is the Cn is Cn is an element of the field, right? It's a scalar, and we multiply n with Cn. So we get confused with uh, it's not combination, permutation combination thing. Okay, so this is going to be just Cn x to the n. Okay, which is equal to just v of x, right? So we thus find that dt minus td acting on this polynomial v and evaluated at the point x is equal to just v of x, which means that dt minus td is the identity operator on v. Okay, good. Now we'll be addressing the following question. For which linear operator T on the vector space V does there exist a linear operator T inverse on the same vector space V such that T times T inverse is equal to T inverse times T is equal to the identity operator on V? Okay. So we are going to ask this question in the next segment. Okay, thank you for attending this fourth segment.